Ladies and gentlemen, welcome to the third session of the day here in the bar room. The next half hour will take a deep dive into the world of ML serving with Ziad Al-Mubayed, staff engineer at Adyen. Let's give Ziad a warm welcome. Ziad, the floor is yours.
Yeah, hi everyone. Thanks for coming to this talk directly before the lunch. So I will try to keep it very fast. I appreciate that you are all here. So I'm a staff engineer at Adyen. I work on the ML infra teams. We build a lot of the tooling that we use for machine learning at Adyen. And one of the things we do is the serving stack. So we try to streamline the process for serving machine learning models. So we're going to talk today a little bit around the practices that we try to enforce at Adyen to ensure like a reliable and performant setup. So the practices we'll talk about today are like very generic things. So I tried not to focus on specific frameworks and like tooling. So very generic things that we can do to have like a reliable and performant setup. But like, why do we talk? So here, like, I also put tech blogs. So if you'd like to check, it's a shameless ad for my blog's website. So, so before we talk, before we dive in, like why we're talking about reliable ML. So, like, we're doing this transition from data-driven applications to more into model-driven applications. So machine learning is becoming at the heart of a lot of today's tooling and use cases. So back in the days, machine learning models were usually like recommending ads, doing ads targeting, recommending friends for you. These kind of use cases were a little bit low error, low cost use cases. So if a model would fail, it was okay. So if I'm like a vegan shopping online and the model tells me, this is a very nice steak. So, okay, it's fine. But the one time this model makes me actually click on this ad, this was a very high reward for this model. So it used to compromise for the failures this models did. So here, like, this is an example of like, buying a toaster and saying, do you want a dark night? So, yeah. So today, these use cases are becoming a little bit more critical with machine learning. So to us, for example, at Adyen, we have lots of use cases that are powered by ML. And some of these use cases are very critical to our merchants. So for example, a risk model misbehaving on a sale that a merchant is doing once a year that they really rely on, blocking their payment suddenly might really take this merchant out of business. So another example, like a payment optimization model doing the opposite, unoptimizing payments might really cause harm and make us lose trust with the clients. So this is why reliability is something we also optimize for in the MLOps team. We don't really only focus on automation and decreasing operations, but we also try to make sure the setup is reliable and performant. So before I like go a little bit into these practices, so I want to talk a little bit about the scale of our setup. So we serve machine learning in almost all over the world. We have like 12 availability zones. We have lots of models online. And we have like around 2,400 ML services running every day. We do like millions of requests, and we have like strict SLOs for the latency. But it's not only about this. So it's not only about the scale. It's a little bit about the complexity. I know that this slide is too much. I couldn't even fit it all in one slide. But like the setup is a little bit complex, and there's like a lot that goes into it. So it's not only about putting services online. There's a lot that also happens. So to the right, you have these services, and there's a lot of them. And each one is like a model that you're deploying. But there's also like traffic routing, there's security, there's authentication, there's service discovery, there's metrics, feature lookups, configuration, like a data scientist also routing traffic online dynamically. So there's a lot that can happen here. We do automate all of this. So there's operations-wise, it's very little. But what I'm trying to illustrate here is that the setup is complex. But it's not only about the setup, how complex it is. It's also like the way how machine learning works. So data scientists are always changing models, and they always want to try to validate theories. So they always want to try to put these models as fast as possible online. So there's always like experimentation is happening online. on production. So we want to make sure the fire doesn't start. So we're going to talk a little bit around reliability and a little bit around performance. In the first part, it will be like few practices that you can do to have like a reliable setup. And the second part will be a little bit around performance. So when I talk about reliability, it's like to have a fault-tolerant setup. We want to make sure our services are available. So once you want to make a prediction, the clients actually can get this prediction. And we want to make sure we have consistent serving. So when I talk about errors or like reliability issues, I talk about like two things. Like technical errors, things can actually like break in your face. So like a service not responding or like exceptions blowing up. But there's also these kind of errors that slip in without you noticing. So for example, like a wrong cast on a type, and then the model does something completely different, like from a float to an int, and then a timestamp becomes like the first of epoche. And then, so these kind of issues, we'll try to also prevent them. Sorry. So the practices we try to enforce is that we want to make sure we have like a self-contained model graph. So we want to make sure things are a little bit more explicit. It's not only that you ship a model and you put it online, but you also need to include like the minimum dependencies or the minimum components that can make sure your model will be reliable online. So we automate a lot of the processes, and these components help us ensure reliability online. So this is like a jar that has not only your pickles, but also like metadata, example requests, input-output schemas, serving dependencies. There's a lot to it more, but I try to keep it simple here and only look at the small components. So we do this to, like self-contained model archives are something that really helps with reproducibility. So it's easy for us to reproduce the models and run them like at different environments. It makes deployments for us much simpler, and we can put them at different environments without any external dependencies. Collaboration becomes easy. So these models can move around. They can be shared to other teammates. They can extend them when they need. And this becomes like almost streamlined. So self-contained model archives have lots of components. And the first one I will talk about is like super underrated, but it's actually example requests. So this is like a very dummy request. It's not actually a model. It's like a dummy model. So this is like here a JSON request, but like there were other use cases and other talk that I saw that they can also package requests for like media images. So it doesn't really have to be this kind of request, but we need to have an example request. So why do we need it? We needed to streamline the testing and integration testing with the clients. So like you saw in the earlier slide, like the model is never online by itself. There's a client that's always talking to this model. And these versions are changing very fast. So to make sure clients are compatible, we use this example request to do integration testing. But not only about this, we have very strict latency requirement. So we can use this example request to stress test these models and see how they will perform online. Example requests make local development very easy. So not very easy, but you can use them to test your models easily online, locally. We use example requests to also warm up services. So something that happens always is like some models have like slow starts. So you put them a service online, or you scale it, but then you see these fluctuations and latencies because the models need some time to start warming up. So we use these example requests to warm up the services and also to do health checks. Yes. So Python, I think we like PyCon, but we all love Python, but Python typing is not very predictable. So I put here like an example, of how typing can lead to inconsistencies. So we have like this dummy model that we just talked about earlier, and it takes like 3 parameters. It tries to calculate from monthly salary, annual salary, and then there's like this cast that happens in between. And we expect this model to perform as we expect, but then suddenly the client starts to, for whatever reason, send wrong types to this model. And Python will just allow this, and things are very fine. So, but as you can see, like in the first request, when it's actually getting like this proper annual monthly salary, the model declines the loan. But in the second request, the salary is the same. The only difference is the type, but the model says, here you go. So this is like a very basic example how types can actually have cause inconsistencies in your serving online. So you can implement type checks by including input-output types. You can implement this like any framework that you like. So like you can use Marshmallow or PyData or Pandera. But this is something we always require, and it has to be part of the model. And we use this to do pre and post checks when we put the model online. So for every request, we check the input, we check the output. We don't really have to break the request, but at least we need to know what's going on. So another thing we also require are dependencies. I think there was a keynote earlier, or like a talk, that the only thing she hates is like unpinned dependencies. So it's also for us. We hate unpinned dependencies. I put an example here. All right, yes, you can see it. So I put an example here of, so when you package a model, you have to include what the dependencies are for this model. But you don't only include the dependencies, you have to pin the versions. So pinning the versions is very important because small change in a version of a library that you depend on can lead to a completely different transformation, which might lead to a completely inconsistent setup. So I put here an example. I'm not sure if you can read it, but it's a small change in Panda's version from 1.35 to 1.40 or 42 can lead to different return times. So in one place, it returns an array. In the original one, it returns a string, and then it leads to an array. So this is something that might slip in or might actually fail online. It depends on how things are running, but definitely something you don't really want. So sometimes you put a model, but you don't want to depend on like dependencies. So your model depends on your repo, and you don't want to include all your repo online. So we allow you or you can bundle sources with your model. So the point here is that we want to minimize external dependencies. And we allow you to package these dependencies inside the model. So the idea is that the model shouldn't have external dependencies. And if you don't specify the sources, or if you don't include them inside the model, either as dependencies with specific versions or inside the actual artifact, what could happen, I put this example here, where, for example, this my transformer that your model depends on might change in the future versions. And then once you unpickle, because it's pickled by reference, then you end up with inconsistencies. And then you end up with completely different transformations. Another thing that might happen is that this transformer might be deleted or renamed. And then it's just going to be an error. So we require that sources are included in the model. If you don't want to put them as a dependency, you can put them as actually inside the model. Or we can also pickle them and include them inside the model. So either both works, and something that can help avoid some issues online. So these are very generic, and I talked a little bit about reliability, but we'll talk a little bit more around performance. So performance, we'll talk a little bit about latency, throughput, and a little bit around memory footprint. So ML code can have a high memory footprint, and yeah, it's not very good. You want to use your resources efficiently. You want to be able to scale when you need. You don't know what will happen when suddenly, like a merchant suddenly decides to make a sale on an item that everybody likes, and everybody wants to shop suddenly. And then you have this spike in traffic, so you should be able to scale when needed. Also, you want to decrease your memory footprint to also be able to use your resources efficiently and also minimize the cost. If not for the cost, for the environment. But I think you should do it. So to look at memory footprint, we always can go back always to the code and look, what are we really putting online? So we try to separate serving sources from training sources. So this is like a very simple thing. I think like most of us use Spark, or maybe if not Spark, some other tool that we use to do like transformations or to play with our data. So it's very easy for us to do something like this, where we put like one file where we have everything inside of it. But this automatically means that online, we will also need all these dependencies. And this increases our memory footprint automatically, increases our images, makes scaling much harder and inefficient. So we advocate for splitting sources, so moving the serving code into its own modules. Then you will only need dependencies for your serving code online. You don't really need dependencies that you are not going to use. This automatically brings down the memory footprint and makes things more efficient. Another thing about memory footprint is Python itself. So when we put our models online, we want to do some sort of parallelism to efficiently use all our resources. So you probably are going to package your model in some server, put it online, and you want to use your cores efficiently. So you don't want to do this. You want to properly use all the cores. And in any language, this usually is fine. The more you scale your service, in theory, the memory footprint should remain the same. And this is something like you would expect in Python also. So you're going to use like some sort of multiprocessing to efficiently use all your cores. You start adding workers, and you think like the memory footprint is going to remain the same. However, in theory, like you will see this with time. So memory footprint will automatically go up, and this is not your fault. It's Python's fault. So it's a combination of how Python works. Yeah, so it's basically around, like I'm not going to go too much into details, but it's basically about reference counting and like how garbage collection works. So the idea is that when you start with a single process and then you fork these processes, the memory is shared between them all. But then every time you reference an object, in Python, it will increment these counters, which are actually mutating the objects, and then copy on write kicks in, and then it moves this object into the other process's memory. So eventually, your memory will be bloated. The more you reference these objects, the more you mutate them, and eventually you end up with like times number of workers, the original memory footprint. So how can you keep things under control? There are a few things we can do. So for example, we can use shared memory. It's not very straightforward, but it works. This involves a little bit copying of data into shared memory, maybe a little bit overhead in the start. It lacks synchronization, but it can work. Offloading your transformations and using data sets, using data structures that are like NumPy data structures helps a lot. These are implemented in C, which means you're not really working with Python. So you don't really suffer from this issue. It's not very easy to, you can't implement everything in NumPys, so there will be a little bit some Python stuff left. So this will go up, but not as much as possible. The third thing is what you can do is restart your workers often. So it's like a small trick that you can do. Every X number of requests, you can configure your servers to gracefully restart these processes. So the memory footprint will go up, but you will keep it under control. So it will not linearly go up. I put some references here. I think they are very nice reads. They talk about this problem. Meta is investing in this immortal object that will hopefully solve this problem. But until then, we have to do these things. So I will talk a little bit about performance. So not really about memory, but more around like CPU. And yeah, so green is good. So here, like I'm trying to illustrate, like if you run a multiprocessing servers, you will use all your cores. And this is something we'd like to do. So we like to keep our work CPU bound. We try to minimize I/O. It's a very nice way to reason about performance, because we can very easily calculate the limitations of our system. We can know how much optimizations are going to increase performance for us. We can do small, like back-of-the-envelope calculations, and we can know what to expect from our system. However, this is not always the case. So this is what you want. but sometimes this is what you get. So you need to make sure you minimize I/O on your workloads. So at least this is what we try to do. So here, like, I added a single log line, and okay, like, it might be different based on the code. So here, what you can see is that the cores are actually doing more system work than doing the actual work that we want, which automatically brings down the throughput of our system. So what we try to do is to keep our work CPU bound. We try to move away I/O. So for example, if you're doing feature lookups, moving them into the client is something good. Here, like, this input-output schemas help a lot, because then you can create a contract with the clients. Look for logging and kill it. And then finally, like, something that really happens a lot is like these future warnings. So if you need to update or if you need to change the version, to mute these warnings, it helps a lot with CPU. So the last point I will talk about is a little bit around latency. So I didn't have like a nice chart to put here, so I took like a dummy chart from our SLO's dashboard. So here I'm trying to illustrate that how we can maintain the latency, so how we can maintain good SLOs for latency, and we stay within our budgets. So there's lots of practices that we can do, but I try to put the generic stuff. Serialization is a problem. We want to minimize it to be doing the actual work. So we can look into fast libraries that do serialization. Compressing requests is something that is useful when you have like a huge request. So when your request is very big, so you don't want to pass it over all the time over the network, the way it is, compressing it, sending it over the network might be faster than actually sending it as raw. Because the time it takes to decompress and compress is less than the time it takes to ship this over the network. So multiply this by billions of requests, and you get a lot of savings. So batch predictions is something that's also very interesting. It depends on the framework. It might be hard to implement. Maybe something that you can pick up off the shelf. But it also improves latency a lot. Sampling for checks. So I talked a little bit earlier about like schema checks. So something we can do is that we can do sampling for these checks. So we don't have to do them on every request. And then we minimize the number of checks we do, but we keep our system in good shape. Staying up to date on Python versions. So for us, like, we switched from 3.6 to 3.8, I think. And then we got like 15 or 20% savings, improved latency, and then like a bump from 3.8 to 3.11, another 15%. Multiply this by billions of requests. This is a very, very good savings on time. Pandas to NumPys, minimizing the use of pandas here. So pandas is very generic. It tries to be very user-friendly, but at the same time, there's lots of things that happen that are not necessary. Switching to NumPys, which is a little bit more specific, will definitely improve latency. So this was it for me. Like, a few takeaways, and I try to keep them little. Less is more. The less you include in your models, or the less you try to do, the more you actually get in the end. Like, being explicit about what you actually package, what you actually put online, in the end results in predictable setups. And minimizing external factors means there's less that you have to worry about and less that can go wrong. So thanks, everyone, for listening. And I hope you enjoyed my talk.